جادك الغيث إذا الغيث هما يا زمان الوصل بالأندلس. قد مضينا ننثر الخير وما نمت الأعين عند الغلس. جادك الغيث إذا الغيث هما يا زمان الوصل بالأندلس. قد مضينا ننثر الخير وما نمت الأعين عند الغلس. إننا مجد وعز إننا عائدون أمتي لا تيأسي.
As I have been invited here as a chief guest, I would actually like to say that I'm still just a child who is driven by his curiosity, who is driven by his passion for knowledge, for understanding this world, for understanding this nature, and for understanding this universe. As we all know that we all have our different drives toward, let's say, whatever field of knowledge, whatever passion. Someone might be really good at music. Someone might be really good at some other subject of physical sciences. Someone might be really dedicated towards his passion of mathematics or other various fields like that. And of course, I acknowledge anyone who is actually striving for knowledge, who is actually trying to fulfill his curiosity. Actually, curiosity is something that you cannot really fulfill. It will always drive you for more and more. You learn something and you will want to learn even more. When I learn Newtonian mechanics, I will now want to learn Einstein's relativity. I learn Einstein's relativity and I'll come to understand what are the flaws in Einstein's relativity, why is it incomplete, and I will want to learn quantum mechanics. When I learn quantum mechanics, then I realize it is also an incomplete theory, and there is still a theory in development that you call the unified field theory, and I will want to work in the field of unified field theory to complete it. So we know curiosity is something that can never be entirely fulfilled. Science or whatever subject you are in, whatever field you are in, it is something that you cannot actually ever complete it or ever be able to completely understand whatever you want to even in your entire lifetime. Be it even the great Albert Einstein, who discovered theory of relativity, who worked in the field of quantum mechanics. But even we know that Einstein couldn't actually achieve what he was striving to achieve, a complete understanding of the universe. Einstein wanted to completely understand this universe and understand this nature. And he spent the last 30 years of his life for a theory which is called the theory of everything or the unified field theory, and he still couldn't discover it. So what we learn from here is that a single person will never be able to achieve it all. A single person is never capable enough to do it all. And that is why we must inspire and we must motivate the future generation so that the oncoming future generation shall complete it. The future generation, the youth of India or the youth of this world shall bit by bit complete everything and gain a complete understanding of this universe, of this nature. And that is why we must inspire everyone, we must motivate everyone in order to do so. And so we can actually strive for better technologies, we can move towards better technologies, we can move towards more innovation, we can move towards a more civilized society and reduce whatever ills there are in our society. Whatever ills there are, say there is discrimination among religion, discrimination among castes, or there are many other things like that. There is terrorism. How do we reduce it all? Only that we have to organize ourselves. We have to be an organized, a better society. And how do you do it? With a more complete understanding of whatever this society is, with a more complete understanding of this universe, of this nature. We need to have better technology so that we can grow in the future. So whatever dangers there are for humanity in the future, be it any asteroid that is coming towards us, or be it any other kind of danger, be it global warming, we can reduce it all. We can, in fact, bring it all to zero. And how do we do it? Only with more innovation. And that is why we must inspire it. Aside from all that, as I had been asked to select a special topic for to present here in front of you all. And what I chose was the special theory of relativity. And why do I choose this specific topic? As I told here, that the more people I can inspire, if I can, the more people I can motivate, the better do I feel for this, that they will bit by bit complete our understanding of this nature, or understanding of this universe. I want to, in fact, tell you all how fascinating the subject of physical sciences, or how fascinating physics is. Let me tell you that in the very beginning, there was Aristotle, a really great philosopher. What Aristotle told us was that if you say you have this mic over here, so if I put this mic on this ground right here, so the mic will actually want to stay on the ground in the same position or in the same state. That is what Aristotle believed. And why does it do so? Aristotle just told us this much, that it does so. There was actually no complete reasoning behind it. What Aristotle told else was that when I try to move it, it certainly moves, but after some time it definitely comes to rest over again. Why does it do so? Because the natural state of this mic will be to be in the state of rest. So what Aristotle believed was that you have any object in this universe, you have any object on this planet at least, the natural state of that particular thing is to be in the state of rest. That was the belief of the great philosopher Aristotle. However, then we come to realize that Aristotle's findings, or Aristotle's philosophy, his natural philosophy, was in fact wrong. The natural state of any object or anything out there is never at rest. In fact, you cannot define what the natural state itself is. What do you even mean by the natural state? Newton comes along alongside Galileo, of course. In fact, it was Galileo who actually worked on these principles, and Newton modified them and developed them more with the law of inertia. They told us that there is no such thing as the natural state. You have the mic, you'll put the mic over here, and it will continue to be in the state of rest because it has a certain property, no matter what object there is out there. So it has a certain property which you call the inertia of this object, that causes this object to maintain this state. If you move the mic, it will continue to move with the same uniform motion, with the same uniform speed, unless you are adding any other external force over here. And here I would like to point out something that we did wrong in our understanding of the universe again. Aristotle understood it wrong, definitely. There were a lot of other philosophers. Newton comes along and gives his first law of motion, which was in fact a modification of Galileo's law of inertia. But for over 300 years, we have been understanding the first law of motion wrong. We have been understanding it incorrectly. And right now, I am not talking about the special theory of relativity. I am talking about the translation of the law of inertia itself. So here, if you look at it, Newton actually wrote his Principia Mathematica, the Philosophia Naturalis Principia Mathematica, which was the single most influential book on physical sciences ever written. When Newton publishes his 3 laws of motion, he publishes his universal law of gravitation. He in fact published the book in the language Latin, which was kind of that language was often used, and in fact most of the scientific text or old scientific texts are actually written in Latin. Nowadays we of course use English as our official language. Of course, if you want to write a textbook, you'll do it in English because most of the people worldwide understand English. But that was not the case back then in the times of Galileo or Newton. So Newton wrote his book in Latin. Now, of course, when we come to our present time, people need to understand the very same book in the language English. So what do? Translate that book from Latin to English. But there had been an incorrect translation for over 300 years. What we have been told in our textbook and what is written in your textbook right now is that Newton's first law of motion states that as long as you don't exert any external force on any body, it will continue its state of rest or uniform motion. What Newton had actually written, because recently I am talking about a discovery that has been made only a week ago. What the original text was, what Newton wrote in Latin, that translates to English as that whenever there is an external force that is imposed on a particular body, that is exerted on a particular body, then the body ceases to be in the state of uniform motion or in the state of rest. Now, what difference does it make at all? If you try to understand, it doesn't in fact make any difference. But what you have to understand is that what is physics? Why do you do physics? To understand this nature, to understand this world. We have to understand this world realistically rather than some sort of fiction. Of course, there are always forces that are being acted on the objects. As I'm standing over here, there is certain work being done on me by friction, of course, as I walk. Because if I walk from here to over there and I return back, you must be knowing that I do zero work. But of course, work is being done by friction. As I'm standing and as I'm walking, I'm counter-effecting the effect of gravity. So there is normal reaction on me, there is gravity on me, there is friction on me. Why then talk about the case of no external forces? That is what you have to understand. What Newton wrote was that there has to be an external force and it causes an acceleration. Not that there was no external force and it causes no acceleration. This is what actually science is about. That you have to understand whatever is happening in your world. And even if there had been a wrong translation, that doesn't still make much difference to our understanding of the world. What actually made difference in this was, I told you, I gave you this one example of a certain incorrect translation. It still doesn't make much difference. What else Newton told was in his second law of motion, the equation F equals ma. So Walter Lewin, in his book For the Love of Physics, writes that F equals ma is the single most important equation in all of physics. Now F equals ma is the equation that caused the Industrial Revolution itself. So you can clearly see the importance of this equation in our daily lives. What if I tell you that the equation F equals ma is wrong as well? And this time I'm not talking about the basically it being incorrect in some sort of translation or anything. The idea behind this principle F equals ma is itself wrong in the context of Einstein's special theory of relativity. F equals ma says that whenever you have any object out there, whenever you have anything out there, be it this mic, when I exert a force on it, it accelerates in what, and it accelerates by the equation itself, F equals ma. What is acceleration? It is a force exerted on this body. In fact, the net force, the total force that you exert divided by the mass, which is what? Which is a measure of the inertia, which is a property to stay at rest or maintain its motion of the body. Now F equals ma, when Newton wrote this equation, he assumed that when you have this object right here, when you have that particular thing right there, when it stays at rest, it has a certain inertia, that is mass of this body. When it moves with a certain velocity, let's try to make it move with a really high velocity, with a really high speed. Let's say 200 kilometers an hour, so that's pretty high. So when it basically moves at that high speed, the inertia still remains the same. What that means is that if I have to accelerate this thing at 2 meters per second square when it is at rest, and if I have to accelerate it at 2 meters per second square when it is moving with over a 200 kilometer an hour, I will need the same amount of force. That is what F equals ma means, a constant mass. That is the force over acceleration ratio, that is mass always remains constant. But now you have to understand, that is another incorrect principle that we had in physics for over 200 years. And then it was the year 1905 when Einstein comes along and he tells us that that is not the case. It is more difficult to accelerate this body at 200 meters per second square when it is traveling at 200 kilometers an hour than it is to accelerate the same body at the same acceleration, 2 meters per second square, when it is here at rest. But the question is that as Newton told us that the concept of an absolute motion or an absolute rest doesn't exist at all. So how can you say that it makes any sense to say the body is moving at 200 kilometers an hour and it will have an increase in its inertia? That is an increase in its mass that Einstein called the relativistic mass of the body. So here you have to understand that oftentimes you are told in your textbooks, that is written in your textbooks, your teacher might tell you that the concept of an absolute motion or an absolute rest doesn't exist. But let me tell you that the concept of an absolute motion and absolute rest does exist. Aristotle was indeed right, but he was not right in the sense that the natural state of a body is rest. Basically, he was right in the sense that there is a concept of absolute motion and absolute rest. And that happens because you can feel your motion. And when do you feel your motion? When you change your motion. So let's say you're basically traveling in a bus. As the bus accelerates in the forward direction, you feel a push in the backward direction. As the bus decelerates, you feel a push in the forward direction. If it changes direction, so you feel a sideways push. Why does this happen? Because the nature wants to make you feel the acceleration. Nature wants to tell you that it is you who is accelerating and it is you who is actually moving in this universe, and the rest of the universe or rest of the ground is indeed static. It means Newton might have been wrong. He was not exactly wrong. Because according to Newton, his first law of motion and even the second law of motion, that is F equals ma, works in certain frames, in certain places that you call the inertial frames of reference. What an inertial frame of reference is, that it is defined to be the place where you can use the first and second law of motion. That is how you define it. As long as you don't change the speed of the place from where you're observing the motion and the rest, so that is an inertial frame of reference. If the speed or direction of motion of the place from where you are observing the entire thing, that itself changes, that is what you call a non-inertial frame of reference. The first and second law of motion were indeed used, and they could be only used in an inertial frame of reference. What that means is that you can actually know when you are in motion and when you are at rest. What about the cases for inertial frame? You can never know the speed with which you are moving or whether you are moving at all, as long as the place from where the motion is being observed is basically changing itself. So if it doesn't change, you cannot know whether you are moving or whether you are at rest. If you are moving, what speed you are moving at. So here comes basically a really great discovery, a really revolutionary discovery in sciences that we call the Maxwell equations. James Clerk Maxwell, who was a really great physicist, and even Einstein himself tells us that Einstein always had a picture of Isaac Newton and James Clerk Maxwell at his desk whenever he was studying or whenever he was working, whenever he was researching on any theory of physics. So we can just by this itself know that how great Maxwell's discoveries had been for the development in the history of physics. What Maxwell discovered was that light, as you see, the light that comes to us from the various stars that you have, from the sun that you have, or the sun's light that gets reflected off the moon, of the surface of the moon, and you observe it at night. All this light that you are seeing over here is actually connected to electromagnetism. And that is another important point that I mentioned over here, that all of physics is indeed connected. You have mechanics, where you study Newton's laws of motion. It is actually connected to the subject of waves, where you are seeing the disturbances in any field. What does a wave itself mean? It means a disturbance. What kind of disturbance? Say you have a medium. We have a medium all around here. What is that? That is air. Now, as I even speak over here, what I am actually doing is disturbing this air here. And when that happens, basically, there are forces and there are motions of all the air particles going on around here. And that is how the sound wave propagates from my mouth over to your ears. That is a wave, a disturbance in a field. It is actually connected to mechanics, and it can be studied using the laws of Newton, using the laws of Galileo, or the laws of mechanics. You have any other subject, electromagnetism, you can indeed connect it to mechanics. And even the subject of optics itself, that is the subject of light, is indeed connected to the subject of mechanics, as you can see over here. Why? Because James Clerk Maxwell told us that it is connected to electromagnetism, in the sense that light itself is a wave and not just an ordinary wave. It is actually an electromagnetic wave. What does it mean to say that light is an electromagnetic wave? You all must have heard this statement that light is an electromagnetic wave. What does it mean? What it means is that in physics you have certain, let's say, how do I say it? Fields, let's say fields. What does a field mean? A field basically means something like this, that you have your space around here, you have your three-dimensional space, the Euclidean three-dimensional space, as long as we are not getting into relativity, where the space is not three-dimensional but four-dimensional. So you have for any object right here. So that is placed over there. If I want to know where it is placed, I need three numbers to know where that particular thing is placed. What are those three numbers? Those three numbers are what I call the coordinate of that particular object. So considering I want to know where the mic itself is placed, what I do is basically assign 3 numbers to it from my position. So a certain number of meters, you might say, certain number of meters in this direction, certain number of meters in that direction, and certain number of meters in the vertical direction upward. And I can know where the mic is exactly placed. That is 3-dimensional space. Now, when you look in your 3-dimensional space, there are certain things like there is temperature. So what's the temperature right now? Let it be anything. Let's say temperature right now is 17 degrees Celsius, for instance. So the temperature right here might be 17 degrees Celsius, but oftentimes it happens that the temperature changes with the position. So for instance, if the temperature here is 17 degrees Celsius and assume that the temperature here is 18 degrees Celsius, it might as well be possible that the temperature here is 19 degrees Celsius. So the temperature changes with your position and with your coordinate in your 3-dimensional space. This is called a field. A field is any quantity or any other number out there that can change with your position. It doesn't necessarily mean to change. It doesn't mean that it will necessarily change. It might be a constant field that it will be the same value at every position in your 3-dimensional space. But it might change. It may or may not change. That's the case. That's what you call a field. In physics, in electromagnetism specifically, you have 2 particular kinds of fields. As you have the temperature field here in a subject what you call the thermodynamics. Thermodynamics is the study of basically heat and its nature. So in physics, that is electromagnetism, where you have electric and magnetic fields. What electric and magnetic fields truly are, it is nothing but a kind of abstract concept. It is nothing more than that. It is an abstract mathematical concept that was given to us by the great physicist Michael Faraday, who suggested the idea itself that you can try to understand that how the forces between certain kinds of charges exist. You have 2 charges, you must have all been knowing about it. You have 2 charges here and here. They exert forces on each other if they are both charged. Positive, positive, they are like charges. As long as you have a like charge, so you will see that they actually repel each other. You have unlike charges, a positive and a negative. They attract each other. How does this happen? It happens with what you called a field. That there is a charge, it creates a field in space. And when it creates a field in space, the other charge that is placed in this field, the field acts on that charge and it basically pulls the charge toward the original, what you call source charge. This is how Faraday told us to imagine this particular thing. That I am standing here, that table is basically placed over there. If I were charged and the table were charged as well, what would happen? I would create a field around me in all this space, and that table, since it is placed in that particular field, the field would act on the table and that table would be either pulled or pushed by me. That is how Faraday told us to imagine this particular thing. Similar to electric field, you have what you call magnetic field. An electric field exists there when any particular charge merely exists. Due to the mere existence of the charge, an electric field will be produced by the charge. Now when that particular charge moves, it has a certain speed. Then there is also what you call a magnetic field. And this is basically the concept of a magnet. Why are certain materials magnetized? Because you basically have inside those materials atoms. And inside atoms you have electrons. Now when the electrons move, since they are charges themselves, electrons carry negative charge. In fact, electrons carry what you call the smallest charge in nature. That is a minus E. E is in fact the smallest charge that you can possibly have. You cannot have a charge smaller than E. Even if charges smaller than E exist in what you call certain particles that you call quarks, actually free quarks can never be observed. The reason is, if free quarks can be observed, so they actually carry, a single quark carries a charge smaller than E, smaller than this elementary charge. It will certainly break the rules of physics. So to protect the laws of nature, the nature abides us into never being able to see free quarks. That is the thing. You'll never observe one quark, you'll never observe 1.5 quark itself. So here what happens, as you have a magnetic field, you might have a combination of electric and magnetic field. You have a charge over here, it moves with a velocity. It will, due to its mere existence, create an electric field. It moves, so it creates a magnetic field. Now what happens that the two fields can combine, and what you have finally is an electromagnetic field. You have an electromagnetic field over here, and Maxwell comes along and writing out four equations that list and that summarize all of the electromagnetism that you're ever going to study. All of the electromagnetism, they can be summarized in just Maxwell's four equations that unified all of electromagnetism. He told that according to his four Maxwell equations, when you create a disturbance in the electromagnetic field, so a charge is moving and it oscillates and it disturbs the field around itself, it disturbs that electromagnetic field. What you have is light or any electromagnetic wave radiating out of the charge. And that is how light is produced. And as simple as that, you can understand that how light originates, how light is indeed produced. The light that comes to you from the sun, what is that? That is nothing but a disturbance in the electromagnetic field that the sun is causing, and that is why from the sun the light is being radiated outward. That is the concept of light is an electromagnetic wave. There are various other fascinating concepts in physics. But if we get on with this particular statement, light is an electromagnetic wave, and proceed forward, now I'll tell you the next big revolution that happened in the field of physics. What basically happened was that when Maxwell wrote his four equations of electrodynamics that summarize all of electromagnetism, they were inconsistent with Newton's laws, or to be more specific, Galileo's laws. Galileo wrote certain equations. In fact, Galileo as well wrote four equations, and I'll tell you what that equation was. Those equations are that x prime equals x minus ut, y prime equals y, and z prime equals z, t prime equals t. Just these four equations. What you call them is Galilean transformation of positions, or maybe Galilean transformation of velocities. Now you do not need to remember the names themselves, and these equations are really basic. So don't basically think that it might go off your head or you may not be able to remember it. You can derive it at any instant whenever you want. In fact, we may derive it right now. How do we do it? That I'm standing right here. I am myself a frame of reference, and if we consider only inertial frames of reference, then it's all good. It's where Galileo's transformation works. Imagine if there were other person. Imagine there were other person standing right here and who would begin to move right here with a velocity or with a speed u. When he begins to move with a speed u and I see him moving with a speed u, what we then do is both look at this particular mic placed over here. Now, if he were to initially stand at the same position right next to me, at the same position at me, and time t later, when he moves in this direction with a speed u, we both were to look at that mic placed over here, and for simplicity, what I'll assume is that the mic is lying along the same line, alright? So what basically happens was that if I measure a position x for the mic, then that moving person will measure position ut, x minus ut with respect to himself. And why does this happen? Because as he moves in this particular direction,
Hello.
I might
Hello. Check. Hello. Hello. 1, 2. Hello.
I might basically measure a position x, but since he has moved a distance ut, he has moved a distance ut towards the mic, so the distance has been reduced for him at least by the amount ut from x, so you have x minus ut. So I measure a position x, then a moving person after a time t will measure a position x minus ut, and that is what you have x prime, the position with respect to himself. So this is how you basically derived. It's just as simple as that, the Galilean transformation. Why did I say that y prime equals y and z prime equals z? Because he is not measuring the position along the y direction or the z direction. He is not moving along the y direction or the z direction. Now, what basically happened in here was that Galileo as well as wrote the fourth equation, that is t prime equals t. Here he told that whatever time he measures with respect to himself, for whatever distance this mic will cover and whatever speed it will have, whatever time units that he takes, it will be the same as my time units. It doesn't matter that he himself is moving. That was the basis of Newton's laws themselves. So all of the classical mechanics is based on the foundation that time remains same for everyone. But when Maxwell wrote his four equations of electrodynamics, the Maxwell's equations, they were actually inconsistent with these equations, with the Galilean transformation of positions or velocities. So what do we do now? Do we discard the new Maxwell's four equations, or do we discard the old Galileo's laws that have been over there for over 200 or 250 years, and all of the classical mechanics and all of the physics is based on the foundation of those Galilean transformation of velocities or position? What do we do now? A good physicist, according to Einstein and according to Brian Greene, is someone who can identify that which laws he has to discard and which laws he has to accept, and which laws will actually explain how, and which will actually help us in understanding our nature and in understanding our universe. So what initially physicists did was that think there must be some error in the new Maxwell equations, since they haven't been even 10 or 20 years old by now, and the Galilean transformation have been there for over 250 years, and the great physicist, the legendary physicist Isaac Newton, based all of his physics and all of his mechanics on the basis of Galileo's laws of velocities or positions. But actually what physicists thought that time was indeed wrong. It was indeed wrong to say that x prime equals x minus ut or t prime equals t or whatever. Maxwell was actually right, and Maxwell equations were indeed 100% correct. There was no fault in the Maxwell equations at all. What this meant was that we have to change our understanding of how we look at space or how we look at time itself. We had to change our understanding. We had to combine the principles of space and time and not look at them as two distinct features of this nature or this universe, but actually a unified feature of this universe, what you call space-time instead of space and time. You don't have to say space and time, because that means you are actually separating the two terms. Space and time are connected to each other. They modify, their laws modify with respect to each other only for a certain combination, what you call the four-dimensional space-time. Now, Maxwell equations were indeed right, and Einstein finally comes in the year 1905, and he tries to explain basically whatever incorrect laws were there for Galileo and those of Newton. What Einstein told was, the first thing, that the mass of a body, as it moves with a certain speed, the mass will actually increase. That is, as the object moves with greater and greater speed, it becomes more and more difficult to accelerate it to greater speeds. And he gave you a certain equation that you call m equals m naught over the square root of 1 minus v square over c square. Now, I'll just tell you that what this equation itself is. It says that if you move with a velocity v, and as you approach the speed of light, that is a universal fundamental speed that in fact that light moves at, all the electromagnetic waves move at. So the mass of you will actually increase, the inertia will actually increase, and you can never actually approach the speed of light itself or be at the speed of light itself. You can never be able to do it. Why can't you do it? Because then the laws of physics might break. Why do they break? Here again we come with another classical understanding of Newton and modify it for the four-dimensional space-time. What it means is that if I move in this particular direction, let me specify, let's say this is the x direction. If I say this is the y direction over here, so you have two perpendicular axes, that is what we normally do in physics. Now, if I move with a certain speed in this particular direction, let me say that speed is v. Now, v can have whatever value, it can have whatever number assigned to it. If I move in this particular direction with a speed v, so I will actually move a distance vt in a certain amount of time t. Now, if I were to, instead of this direction, move in this direction over here at 45 degrees to this, then what distance do I cover? I still cover a distance vt, but in this direction. Now, what I do is use the basic laws of trigonometry and basic laws of vector. In fact, it need not be even vectors. You don't have to understand vectors to understand what I'm saying. What you have to understand is that when I move a distance of vt in this direction, it means I am basically moving a distance of vt by root 2 in this direction and vt by root 2 in this direction. So a combination of vt by root 2 in here and vt by root 2 in here gives me a vt in here, because it is 45 degrees. Now, what this means is that if I move in this direction at a speed v, then I move a distance vt in time t, but if I move a distance a distance of Vt in this direction with a speed v. Then I move a distance Vt by root 2 in this direction and Vt by root 2 in this direction. So when you move at a certain angle to the axis themselves, then you reduce the distance or you reduce the overall speed that you have in that particular direction. This is our Newton's understanding of this world, and it is actually correct whenever we look at it. But now you have to understand it, how to modify this understanding for our four-dimensional space-time. What Einstein told us that we are indeed, everyone is moving in space-time, is moving in time at the velocity, speed of light, at the speed of light, 3 times 10 to the power 8 meter per second. And right now, even when I'm standing over here or when you are all sitting over there, we are actually moving at the speed 3 times 10 power 8 meter per second. But through what? Through space? No. We are all moving through time. The speed of any object through time, the natural speed is 3 times 10 power 8 meter per second. Now, when that particular object moves at speed c, that is 3 times 10 to the power 8 meter per second through time, and also that object will move in any specific direction through space. As I walk over here, then the speed of me from time or through time shall reduce. That is what it means. Because when I move at a specific angle, when I move in two different directions, that gives me a combination of those two, then the speed of me through one of those directions will certainly reduce. As it happened from Vt over here, let's say V to V by root 2 in one particular direction. When I move both through time, which we are all doing, and through space as well, when I move through space and I am walking around here as well, then my speed through time reduces. And when my speed through time reduces, it means time for me slows down. That is what happens, and that is the concept of time dilation. It's as simple as that. Let me tell you, special relativity, as perceived by many, is indeed not such a difficult theory. All you have to do is modify your understanding of three-dimensional space-time to a four-dimensional space-time. That is all you have to do. The mathematics of special relativity, when written down, is really simple, is extremely simple. In fact, it's extremely simple that even if you have just studied basic high school mathematics or even mathematics until 8th grade, you can still carry out the mathematics of special relativity. It is as easy as that. But why then did it take 200 years to actually come to this conclusion? Because nobody was indeed willing to accept the fact that we are moving through time at this certain speed, or willing to change their perception of space and their perception of time. That is what was happening. So we should always be willing to understand this universe more by modifying our previous understanding, by changing and by learning new things, by changing whatever we have already learned. We should always be ready to change our perception of space and time. If scientists were indeed ready to change their perception of space and change their perception of time, change their perception of inertia, that they actually believed inertia stays constant, but no, Einstein told us it increases with increasing speed, then we would have a special relativity right when we had Newton's laws, but we didn't. We got it after 250 years. And even right now, as I speak, we don't know what other incorrect laws that we have right now. Remember always, physics is never wrong. Physics is never wrong. It's just the theories that have been given to you by physicists might be wrong. Physics always stays correct. It always stays right. Now, it might be the case that the most advanced theory that we have in physics right now, it's a theory that you call the quantum field theory. It might be the case that quantum field theory is itself wrong. What if quantum field theory is indeed wrong? What if that is the case? Does it mean physics became wrong? If quantum field theory was wrong, it was never physics in the first place. That is the thing I'm trying to tell you. Physics is never wrong. It's the theories that have been given to you by physicists can be wrong. And indeed, most of the time, as we study physics, as we study further and further, we realize that whatever you have been told until now, or whatever have been written in textbooks in various scientific literatures or scientific texts, have been wrong for all this time, have been wrong for hundreds of years or for thousands of years. Now, as Einstein told us that the mass increases, the time slows down as you increase, the mass increases as you move through with a certain speed. What else he told us? That your length along your direction of motion shall contract. That is what you call a Lorentz contraction, or in simple terms, just a length contraction. that as I'm moving right here, if I were to move with an extremely high speed, only then can I notice this effect. Otherwise, you can clearly say that I'm experiencing a length contraction. So whatever direction I'm moving, in that certain direction of motion, I am actually being contracted. But these effects are only seen when you're moving close to the speed of light. Why is it only seen when you're moving close to the speed of light? Because when you move close to the speed of light through space, then your speed through time reduces a lot. And when your speed through time reduces a lot, only then you can actually notice these effects. Or otherwise, if you're moving at a relatively low speed to the speed of light, then your speed through the time dimension will not change much, and you won't even notice this effect. That is what basically happens. In order to experience these effects, you have to be able to move towards the speed of light. Now, how do we do it? We can use certainly what you call an LHC, a Large Hadron Collider. It is basically a system where you accelerate the subatomic particles to really high speeds, to speeds that are close to the speed of light. You can accelerate an electron or a muon close to the speed of light. And there you actually see this particular effect happening, that they are being contracted or the time for them slows down. How do we know that the time for them slows down? Let me tell you that there is a certain particle that decays really quick in physics. That is what you call a muon. Now, it has a certain really less time period assigned to it, that if it is created right now by certain disturbances, of course, it might be decayed just the next instant. But what scientists did was, what physicists did was create such a particle, or at least observe such a particle. And when they looked at the time that it needed to decay, it was really a large period of time. And why was it so? Because the muon was actually moving, and it was moving really quick, close to the speed of light. So in the muon's frame of reference, in its own frame of reference, the time was really, let's say, for a certain instance, for a certain number of microseconds. But for the time for us was different, since the time for him was slowed down. So if that is a certain number of microseconds, for us it might be a millisecond, or it might even be few seconds, because the time for that was slowed down. It operates only according to its own perception, its own understanding of time. And that is why it lasted this long for us, but it lasted only a few microseconds for itself. So if you're moving in a spaceship that moves close to the speed of light, so let's say whatever biological processes are occurring, whatever as you're breathing and as the blood is circulating in your body, even those processes slow down. But will you feel those processes being slowed down? Will you see those effects being slowed down? Actually, you will not. So let's say, for instance, a kind of cancer development. For you, it will again take the same amount of time. For you, it will again feel the same. But for us, who is observing you from outside the spaceship, he will see that no, the cancer development has indeed slowed down. That is what we actually see. This was all the new kind of physics that was developed, that you call the modern physics. That was the Einsteinian physics rather than Newtonian physics. But what if I tell you that special relativity is again wrong? Things really don't happen that way. Or even if it is not wrong, special relativity itself is an incomplete theory. And Einstein himself said so, and he himself proved so. Because according to Einstein, no effect or no body can come close to in fact, it might come close to the speed of light, but it can never cross the speed of light, or it can never actually equal the speed of light. But then again, you have another conflict between Einstein's and Newton's theories. And what is that? That is the concept of gravity that you have. The concept of gravity is something like this. You have two objects around here. They will attract each other with a force that you call the gravitational force. Now, when they attract each other with a force that you call the gravitational force, that depends on how far the two objects have been placed. What I do is pick this object from over here and place it at a farther distance. And as I place it at a farther distance, according to Newton's laws, the gravity changes. For a farther distance, the force is reduced. If I double the distance, the force is reduced to 1/2. This is what you call an inverse square proportionality. If I triple the distance, the force is reduced to 1/9. If I increase the distance by 4 times, the force is reduced by 1/16. Now, when the force is reduced, according to Newton, it is reduced instantly. That is, you have an instantaneous effect. As you change the distance, the force changes. But according to Einstein, the information or the influence from one body to other shouldn't actually be able to travel faster than light. But according to Newton, it is an instantaneous effect. That is an infinite speed effect. It travels instantly. So what is the problem over here? Einstein, in a letter to his friend, himself said that special relativity was indeed a child's play compared to the theory that he was developing now, a complete theory of gravity that includes both the Newtonian mechanics and the special relativity. And after 10 years of effort, when Einstein discovered the theory of special relativity in 1905, finally, in 1915, Einstein comes along with the most advanced theory of gravity that we have right now. And that is what you call the general theory of relativity. And what Einstein told in general relativity was another shocking thing that you find over here that changes our perception of, again, how things work in physics, in this nature, in this universe. Gravity is not a force. That is what Einstein told us. Gravitational force was, in fact, gravitational force would be a wrong term to coin over here, because gravitational force itself remains no longer a force. Einstein told us that it was never a force. We had been understanding it wrong. As the apple fell and Newton saw that the apple is falling, there is a force between these two objects. No, it is not a force. Now here the physics that I am going to present in front of you is much more complicated when you compare it to the simple, what Einstein called a child's play, the special relativity. What Einstein told us that as a certain mathematician told that the dimensions that you have around you, these aren't just 3 dimensions, but rather 4 dimensions, and you don't have a 3-dimensional space, but as according to Einstein himself, you have a 4-dimensional space-time. You have a fabric of 4-dimensional space-time all across your universe. It's basically a fabric of 4-dimensional space-time all across this universe, is spread all across this universe. What happens that whenever any particular object is placed in that fabric, it curves the fabric. It is basically something like this, that whenever you have a fabric laid out, you put a certain heavy ball on that fabric, you will see it basically curves the fabric in the downward direction. Einstein told the similar thing. Assume you have a fabric of space-time itself is spread all across the universe. We are all placed in that fabric right now. We are all standing or sitting in that fabric right now. And what is happening that as we are placed in that fabric right now, we are curving the fabric in the downward direction. And when we are curving that fabric, when you place a heavy ball on a fabric and the space around it curves, the length around it curves, and you place another ball, a smaller, lighter ball in that curved space, it directly falls toward the original ball. It is attracted towards the original ball. And that is what gravity is. You have a fabric of space-time all across this universe. You have another lighter object placed in this curved fabric. It will clearly be attracted to the thing that originates this curvature. And that is gravity. Gravity isn't a force, but it is a curvature of space-time. And this space-time, this fabric is what? It is the fabric of a space-time. Now, as Newton had told us that space is not absolute, time is not absolute, Einstein tells, yes, space is not absolute, time is not absolute. They are relative. Space is different for different persons, because length is being contracted, time is being dilated, time is different for different people. But space, time, that is a combination of space and time, is the same for everyone, because everyone are right now sitting and standing in the very same fabric. All these planets that move around the sun, why do the planets move around the sun? Due to the force of gravity? No. The planets are moving around the sun because the sun curves that fabric, and the planets placed in that fabric are being attracted to the sun, and that is why they actually orbit around the sun. That is the theory of general relativity, which is kind of a really advanced theory, and further information in general relativity itself requires really advanced mathematics. And I'll tell you how advanced mathematics that Einstein himself did not know that what mathematics he has to put in his theories. When Einstein thought of this, the concept of fabric of space-time, or a certain postulate in the general relativity, what he called the principle of equivalence, then although he could figure out how things are working on a physical and conceptual scale, Einstein couldn't figure out that how he will write out these things mathematically. So he had to ask a fellow of his, a friend of his who was indeed a mathematician, if such a mathematics exists that will help him write the theories, write the mathematics of these fabrics and these space-time. And then that friend, even who was certainly a mathematician himself, had to search a lot, search a lot, and search a lot. And finally, he came up with what you call differential geometry. He finally came to know that there exists such a mathematics, and Einstein and that friend of his who was indeed a mathematician themselves had to learn this subject of differential geometry. When Einstein learned it, then only he was able to present the general relativity in front of everyone in the year 1950. So from that only we can learn how advanced theory general relativity is. But the problem is that right now, as we speak, there is trouble in general relativity itself. It is also an incomplete theory, and that was the last task that Einstein wanted to achieve in physics. What Einstein wanted to do was a complete understanding, achieve a complete understanding of this universe. So he realized that general relativity is an incomplete theory in the sense it doesn't actually, it actually contradicts a latest theory that was the quantum mechanics. Now, quantum mechanics is really a bizarre and strange theory. It is a really weird theory. It works on an atomic and subatomic scale. When Einstein thought of his general relativity with alongside quantum mechanics, he saw that the two theories, actually the two kinds of physics on which all of the modern physics lies, or based on its foundation only, that two physics contradict each other. If you have general relativity right, so it might be the case quantum mechanics is wrong. If you have quantum mechanics right, it might be the case, or it is the case, that general relativity is wrong. So the two of them are contradicting each other, and both cannot be right simultaneously. So what do we do now? Achieve a more complete understanding of this universe, of this nature. You need to develop such a theory that will be consistent with both, or that will modify both the general relativity and quantum mechanics. How do we achieve such a theory? We don't know yet. We don't know how are we going to find such a theory. And this is what you call the holy grail of theoretical physics. The holy grail of theoretical physics right now is to find this theory that you call the theory of everything. The theory of everything, a single theory that explains everything that you see in the universe, everything that can be witnessed in this nature. It will explain every single thing out there. That is what you call a theory of everything, or you might call it a unified field theory. Einstein has spent the last 30 years of his life for achieving this theory. He could not do it. There are many other physicists who worked a lot for this particular theory, like the great Professor Stephen Hawking, who had been an inspiration for me as well. In fact, when I read Stephen Hawking's book, A Brief History of Time, which is his international bestseller, that was the thing that inspired me to work in physics, or to study physics, to try to understand. That was the first book I read, and that was basically the book that brought me into the field of physics. Hawking himself devoted a long lifetime in this particular subject, his entire lifetime in this particular subject, but couldn't accomplish this particular task of finding a complete unified theory, a unified field theory, or a theory of everything. So what it has to certainly do is combine, or rather modify, both the general relativity, which works on large scales, the scales of gravity, where gravity is effective, and quantum mechanics, the theory that is really weird and peculiar, that works on a small and subatomic scale. Let me tell you a little bit of how quantum mechanics works. It works in somewhat this sort of way, that although in physics we always want to find the future state of something, I always want to find where that mic is lying or where that table is lying. Quantum mechanics tells us that you can never be exactly able to tell where that mic is put or where the table is lying. That is what quantum mechanics is about. What it says is that all you can find for a particle or for a body is the probability that you'll find that particular thing over there. So you can only find a number that tells you that how likely you are to find that particular table lying over there. But as we speak, I'm seeing that table right over there. So how is it possible that I cannot know the position of that? So what the answer to this is that when we turn off all the lights, and we remove all the interactions, and we are not seeing that table right there, I ask the question, I have turned off all the lights. Is that table still lying over there? That is the question I ask. Or I may ask even more grand question. When I turn off all the lights and when I don't see the table, does it mean that the table exists at all? Does it have any implication on this that the table exists at all? Can we actually ask this question? The answer is yes, we can ask this question, but we cannot exactly find the answer. That when I turn off all the lights and when I don't look at the table, whether the table is lying there or not, I don't know. Whether the table exists itself or not, or whether it ceases to exist, it ceases of its existence. I don't know. We cannot know as long as we are not looking at that. So even if I'm looking at that, the light that is coming and that is being reflected from the table and reaching into my eyes, it disturbs the table on an atomic and subatomic scale. Why does it do so? Because the particles of light strike the table, and as they strike the table, they give a certain amount of energy into the table. It might be relatively low to the ordinary energies that we have over here, but it disturbs the table on an atomic and subatomic scale. Due to this particular disturbance, I can never exactly measure the exact position of that particular table. You can never do it. So I am telling you one particular point to always keep in your head, that physics has already given up on finding where a particular object is lying or with what speed it is moving at all. That is the inconsistency of general relativity and quantum mechanics. Although whatever things that I have discussed of quantum mechanics over here as of yet works only on an atomic and subatomic scale. This actually deals with electrons instead of mics or instead of tables. That whether you can know whether the electron exists there or not when you are not looking at it, or how the electron behaves or moves when you are not looking at it. There are so many weird conceptions in quantum mechanics that we know as of now may be right, and indeed as of whatever experiments have been done right here, and using the help of quantum mechanics, whatever inventions and innovations have been there, we know that quantum mechanics is indeed right. It makes no sense to speak of the electron when we are not looking at it or when we are not observing it. Indeed, it might be the case, there is a certain interpretation in quantum mechanics that, let's say you have over here a particular screen or maybe a particular wall or barrier. You have a stream of electrons flowing into the barrier. Now, some of you might be knowing about this particular thing, what you call Young's double slit experiment. This was done with light waves, but let's do it with electrons. If this particular barrier has two slits over here, a close distance apart, and over there a screen. All right, over here, let's say a screen. Now, when the stream of electrons passes through the two slits, as we look at the electrons and we observe them on an atomic and subatomic scale, I might say that this electron passes from the first slit and goes and hits the screen on this place. This electron passes through the second slit and it hits the screen at this place. When I turn off the lights and when I don't look or don't observe the electrons, how does it pass the slits then? Then comes along an interpretation of quantum mechanics that it might be the case the electron passes from one slit, it might be the case it passes through the other slit, it might be the case it goes through one slit, then it goes in a cyclic path, it goes back to its original position from the second slit, then it goes back through the first slit and hits the screen again. Then you might as well say that the electron doesn't pass through the slit. What it does is, first of all, go around in interstellar space, it revolves around galaxies and it crosses the entire universe, and after making a journey through the entire universe, the electron comes back to the position again and it passes through one of the slits and hits the screen. So although peculiar it might seem, but these interpretations might actually be true when we speak of quantum mechanics. And this is why I told you that quantum mechanics is such a weird theory, because it doesn't match, it actually contradicts whatever intuition and logic we have of our nature around us, but it is indeed true in atomic and subatomic scale. And that is why I told you that physics has already given up on finding where that particle is or where it has to be in the future. What it can only find is the probability of where the particle is and where it is going to be in the future. And that is the current holy grail of physics, is to combine these principles and these interpretations with Einstein's general relativity, that the theory of gravity, the theory of space-time, and form a complete theory, the unified or the theory of everything that will complete our understanding of physics and this nature. That is what I had to tell all of you in order to fascinate, if I can, all of you, to tell you how interesting the idea of physics or the idea of these theories and interpretation themselves are. As when we come from Aristotle, who told us that the absolute state of every object is at rest. Then comes along Galileo and Newton, who told us that this is indeed wrong. Then comes along Einstein, who proves even Galileo and Newton wrong. And then comes along the works of Werner Heisenberg, Niels Bohr, and Max Born, and many other great physicists like Richard Feynman, who developed quantum mechanics, all combining all of their efforts, and they told that Einstein was indeed wrong, and now we have to move towards a physics that is beyond Einstein himself. That is the physics we have to move towards now. And that is why we must inspire and we must motivate, so that all of you one day must inspire and motivate more and more people, that someone who will be inspired and motivated by this current generation may in future find such a complete theory and may add to our understanding of this universe and our nature. That was all I had to say right now, and thanks to you all for having the patience to hear out.